Hello everyone, welcome to my channel and welcome to another video on integration. I have two integrals in this one. The first one is this one. We're required to prove that the integral from -1 up to 1 of the square root of 1 plus x all over 1 minus x dx is equal to pi. How do we approach this? Well, here is how we approach it. Our first integral is the integral, and a definite one, from -1 up to 1 of the square root of 1 plus x all over 1 minus x dx. We ignore the limits of integration first. We will come back and use them at the end. So this basically implies we are dealing with now with the integral of the square root of 1 plus x all over 1 minus x dx indefinite. This simplifies to the integral of the square root of 1 plus x divided by the square root of 1 minus x, and we're going to say dx. Now notice square root of the whole fraction is equal to the square root of the numerator divided by the square root of the denominator. At this stage, I'm going to introduce the special one that I've already spoken about, which is square root of 1 plus x there all over square root of 1 minus x. We're going to multiply this by square root of 1 plus x divided by square root of 1 plus x. There is your special one right there. And then we have dx. Now, we combine the numerators and denominators, taking us to page 2 as follows. So that will be equal to the integral of, watch this, square root of 1 plus x times square root of 1 plus x, and then we're dividing this by square root of 1 minus x times square root of 1 plus x dx. Now in the numerator, you'll agree with me that we just have square root of 1 plus x all squared all over. In the denominator, we have square root of 1 minus x times 1 plus x dx. In the numerator, this cancels that. You'll agree with me that what we have now is 1 plus x in the numerator. In the denominator, we have square root of, check difference of two squares there, 1 minus x squared, and then we have dx. At this stage, I'm going to use what we call term-wise division. So this is going to be equal to the integral of 1 all over square root of 1 minus x squared dx, and I'm distributing that and that, plus the integral of x all over square root of 1 minus x squared dx. Right, term-wise division, we divide this into 1 and into x, and obviously there's a plus sign there, there it is, and we distribute dx and the integral sign as follows. Now I'm going to call this integral 1, plus I'm going to call this integral 2. So we have to evaluate I1 and I2 separately as follows. We put this aside. So what we have now is I1, taking us to page 3 here. Right. So I1 is equal to the integral of 1 all over the square root of 1 minus x squared dx. We need to evaluate this, where when you see the square root of 1 minus x squared, trig substitution and sign to be specific comes into mind. So we're going to say now, let sine of theta be equal to x. Two equations must come from this one. The first one is we have to solve for theta. So theta will be equal to sine inverse. Sine inverse, some people say arc sine. Let me remove this part here. Sine inverse or arc sine of x. I'm going to put x here. Come and put brackets later. The second equation there that comes from there would be, we're going to differentiate the left-hand side and the right-hand side implicitly with respect to x. So differentiating this, basically I'm saying d dx of sine theta, the answer must be equal to d dx of x. Now here we're going to use chain rule, differentiate sine first, we get cosine of theta, and then we're going to say times d theta dx. On the right hand side, derivative with respect to x of x is 1. You agree with me there? Multiply both sides by dx, we're going to get cosine of theta, d theta is equal to dx. Fantastic. Now let me just put this in brackets there, like that. Now, what do we do next? Well, that integral then changes as follows. It changes to the integral of 1 all over, check this, square root of 1 minus sine squared of theta, and then we're multiplying by, instead of dx, we're going to say cos theta d theta. Cos theta d theta, like that. Moving on, taking us to page 4. Now, what we have is the following. So what we have now is the following. Remember, 1 all over the square root of 1 minus sine squared. Remember, it's cos squared of theta, and then we have cos. Cos there. We have cos of theta. Let me fix this up. It doesn't look very nice. Times cos theta d theta. Cos theta d theta. I'll fix that one up shortly. Taking us to the next step, we're basically saying this is 1 all over. What is square root of that? We take the positive square root of cos squared theta, positive square root, so we get cos of theta. And then we're going to say this part here is cos of theta, and then we have d theta. Remember I said here, this is cos of theta, d theta. I want to make sure that that one is clearly written so everyone can see. So this is cos theta d theta, like that. Now, notice something. These cancel, and what do we have? We have the integral of 1 d theta, and obviously you'll agree with me that this is theta. Let's move back up here on page 3. Theta is what? Sine inverse or arcsine of x. So this is exactly equal to sine inverse of x. So I1 evaluated. Now we're moving on to I2. I2 taking us to page 2. If you notice, I2 is this part here. So I'm going to have to work on this one now. So I'm going to say I2, we know this is the integral of x all over square root of 1 minus x squared dx. When we look at this expression here, you see there's x squared there, which after differentiating, it will give you 2x. So we have x in the numerator, which means this integral can be rewritten as 1 over square root of 1 minus x squared, and then I'm going to say x dx. At this stage, I'm going to let u squared be equal to 1 minus x squared and proceed as follows. So, taking us to page 5, now we're now saying let u squared be equal to 1 minus x squared. Differentiating both sides implicitly, if I may hurry up now, we have 2u du. The answer on the right hand side will be minus 2x dx. Remember, derivative of 1 is 0 because it's a constant. Divide by minus 2 both sides, you have minus u du is equal to x dx. Now, this part here is this part here. Therefore, this integral changes to, if I move it down like this integral will change as follows. We're going to say that integral changes to the integral of 1 all over. Remember, u squared equals this. So it will be square root of u squared. And instead of having x dx there, I'm going to have minus u du, like that. Now let's simplify this part. Take the positive square root of u squared. And what we have is, and take minus out, minus the integral of 1 all over u times u du. These cancel, and what do we have? We have minus the integral of 1 du, and that's minus u. Now let's move back. Notice something here. Two equations we can also obtain from there. The first one would be take positive square root of u squared. The answer will be equal to, also on the right hand side, positive square root of 1 minus x squared. And the second one is this one here. So this is one we need here. So this will be minus square root of 1 minus x squared. So that is I2. Now we must move back. Where are we at now? We are here. So we know I1, we know I2. Our integral, indefinite integral, has been evaluated. Which one? This one here has been evaluated. Now we must take limits of integration into account. So now we're going to say, taking us to page 6, now we're going to say, let me move this up. I just want to see where my I1 is. I1, we said sine inverse. It's actually on page what? Oh, here we go. On page 4. I1 is this one here. Remember, we're coming from page 3. Let me just take you to page 3. There is your I1 equal to that. We evaluated that to sine inverse of x, or arc sine of x. And I2 is this one here. So basically, to conclude this and evaluate our integral now, we are saying, therefore, the integral from minus, first I'm going to take the indefinite one, integral of 1 plus x all over 1 minus x dx is actually equal to sine inverse of x, and we have minus square root of 1 minus x squared. Notice I'm just putting these two together. That one, which is this part here, and this one here, which is our I1 there. Now we must consider our limits of integration. Limits of integration are from minus 1 to 1. So I'm going to say, therefore, the integral from minus 1 to 1 of the square root of 1 plus x all over 1 minus x dx will just be equal to this one here, sine inverse of x evaluated from minus 1 all the way to 1. And then I have minus, and I'm going to use brackets here now. Square root of 1 minus x squared evaluated from minus 1 to 1, like that. And this part here, this is sine inverse of 1 minus sine inverse of minus 1. And then I'm going to say minus this part, if you like, it's going to be square root of 1 minus, if you put 1 there and square it, it's going to be 1. And then minus square root of, if you put minus 1 there, it has to be squared, so it will be 1 minus 1 as well. This part here, sine inverse of 1 is pi over 2. Minus sine inverse of minus 1 is minus pi over 2. And then here we have minus 0, which is 0. And this part, you'll agree with me, it's pi over 2 plus pi over 2. And then we have minus 0. You can agree with me that this is basically pi. So we have actually proved our integral here, that this integral here evaluates to pi. As you can see down here, our final solution is pi. So this is how you go about this one. Now I'm moving on to the second integral I have in this video, which is an indefinite one. It's this one here, and I hope I can be fast enough. Yeah, there it is. The second integral, it's the integral of dx all over 4x squared plus 4x plus 2. We're supposed to evaluate this. Now, this is an indefinite one. There are no limits of integration there. Now, the approach doesn't change. So our integral number 2, we start from dx all over 4x squared plus 4x plus 2. Now, if you look at the denominator here, differentiating this, it will give you 8x plus 4. And we don't have such an expression in the numerator, which means we have to work on the denominator. And it being a quadratic function, we have to first of all think of completing the square of this one. And therefore, looking at 4 and x squared there, I'll be tempted to say, check this, let 4x squared plus 4x plus k, some unknown k. I'm going to ignore the 2 for a moment. This can be rewritten as 2x plus some constant a. We square this. The square root of 4 is 2. Square root of x squared is x. And I want to expand that, and then I'm going to equate coefficients. Let's move back here. So we're saying 4x squared plus 4x plus some constant k equals, expanding this, you're going to get 4x squared plus 4ax plus a squared. Now you see the first part is taken care of. The central part, we're going to take 4a and equate it to 4. Coefficient of x on the right equal to coefficient of x on the left. So we're basically saying this implies 4a equals 4, and the constant term k is actually equal to a squared. Solving for a here, you agree with me, a equals 1. And bringing it to this side, k will be equal to 1 squared, and the answer is 1. So therefore, I can say, therefore, check this, 4x squared plus 4x plus 1, because I know now the value of k is 1. I'm putting 1 there, and I'm saying this is exactly equal to 2x plus, what's the value of a? 1, and it's all squared. Now notice there is a 2 outside there, so which means I can rewrite this integral as follows. I'm going to say that integral now is equal to the integral of dx all over 4x squared plus 4x plus 1 plus 1, like that. This part here is taken care of, as you can see from there, will be replaced by that, and then I'm going to say plus 1. So taking us to page 8. Page 8, what do we have now? We're saying that this part, this integral now changes as follows. Now we're saying that integral changes as follows. So we're saying that integral is equal to the integral of, and I'm going to rewrite the whole thing, 1 all over. This part I'm going to say 2x plus 1 all squared, and then I'm going to say plus 1, and then I'm going to say dx there. Fantastic. At this stage, looking at this expression here in the denominator, and I have 1 there, tan substitution comes into mind. So I'm going to say let tan theta be equal to 2x plus 1. And I'm going to have to differentiate implicitly both sides. Differentiating tan theta, you get sec squared theta, and then we're going to say d theta here is equal to derivative of the right hand side there, just going to be 2 dx, if you agree with me. Derivative of 1 is 0, it's a constant. Derivative of x is 1 times 2 is 2. I'm going to have to differentiate, divide both sides by 2, so I have sec squared theta, d theta all over 2. This is going to be dx. That's the first equation I'm going to obtain from there. The first equation is that. So the second equation, I'm going to actually solve for theta. Solving for theta, I have theta equals arctan or tan inverse of 2x plus 1. I'm going to need that at a later stage. All right, now let's transform this integral then. That integral transforms into the integral of 1 all over tan squared theta plus 1. Instead of dx, I'm going to have this expression is equal to dx, remember? So times sec squared theta, d theta, we're saying all over 2. Now 2 is dividing, take it out. So this is 1 over 2, the integral of this here, tan squared plus 1, you must have seen it from my previous videos, that this is basically sec squared theta, and we're multiplying by sec squared theta d theta. Yes, these cancel, taking us to page 9. What do we have on page 9? So page 9, what we have is this integral now simplifies to, if you check, it will be the integral of, it will be 1 over 2 times the integral of 1 d theta. Now integrating 1 with respect to theta, you'll agree with me that this is just theta. What is theta equal to? Here it is, tan inverse of 2x plus 1. So this is actually equal to 1 over 2. Remember, this is an indefinite integral. We have to say plus a constant c. So this is half of tan inverse of 2x plus 1. And then we have to say plus a constant c. So this is how we complete this integral here, an indefinite one. And that's the work I had for you in this video. Two integrals that we've looked at. The first one was a definite one, requiring us to prove there it is. The second one was this one, an indefinite one, requiring us to just evaluate this integral. And looking at the denominator there, we were able to rewrite this first by completing the square and then using tan substitution, and we managed to get to the answer. All right, if you're new to this channel, support us by subscribing. Your feedback remains very vital for us. All right, I'll see you in the next one.